Okay, another things that you need to know is what is cost function. Okay, I think you have some exposed to the element of cost function in your previous lectures. However, this one I would like to elaborate more about this cost function. Okay, if you remember, one way to find out, okay, to identify whether your linear regressions equation that you have been produced is fit with your data is through R square. Okay, if you remember, I bring the slide here. Okay, this is the previous slide. That is one of the mechanism that you can use. Okay, one of the approach that you can use to check whether your linear equations is fit with with the given data. But in general, there's another mechanism also you can use in order for you to know whether your produced linear regression formula or linear regression function is fit with your data, which is called as a cost function. Okay, what is cost function? Okay, one of the mechanism or one of the way to compute this cost function, I think you have done this one before. Okay, for example, you have this kind of data. Sorry. Okay, you have this kind of data, and then this is your data. And once you identify certain formula or certain function that represent your linear regression, okay, let's say this is the data that you may manage to produce based on you set your own beta there. Okay, doesn't matter it's beta or not. Okay, this one you will only, okay, of course this in this example should be y equal to beta naught plus beta 1 x1, because this is your x1 and this is your y. Okay, this axis is your y. Okay, this is your y. Okay, you only have one features. So in order for you to find whether your linear regression here is fit with data, how goodness it fit with your data, so in one way, I think you have done this before. You are measuring the errors there. Okay, for example, this data, this is the actual data, but the predicted y head here, or the predicted y here is at this point. So once what you do is actually you are measure the distance here between your actual data and predicted data. So that is called as your E, or your errors. So let's say this is the first errors. Okay, let's say okay, this is the first error because this is a post point. Your let's say this is the first data. Okay, I don't want you to confuse with this one. I just put x. Okay, not x1. Okay, just x. Just put here x. Okay, just assume this one is your x1. So your at your x1, your predicted y is this one, this point, and your actual y1 is this one. So in other words, if you measure the errors there, let's call the error is as a E1. So this one is E1 and this one is E2. You measure this one, this is E3. So if you collect all the errors, then you can set in this form. Okay, where the E's there, okay, the bold E there is actually is equal to all error happen at this data. Okay, from E1 until N. Okay, of course, if you talk about the previous example where our data set is 1000, then that's mean your N here is from E1 until E1000. Okay, that is the matrix represent this bold E, where that is called as a error vectors. So if you extend the definition of your errors there, this is how it's look like. Meaning that this is your actual y1 and this is actually your predicted y1, or we call as a y head 1. Okay, y head 1, and this one is y head 2. Okay, this one should be n. Okay, there's a mistake there. Okay, so if you separate it into separate matrix, then this one can be one set of a matrix. It's a subtraction operation between two matrices. Okay, how you get this one? Actually, this one is from the previous slide. Okay, if you talk about the definition of your linear regression, or your F there, is this one. Okay, so that's how it should be here. So in other words, if this is the how we represent it in matrix form, then you can also represent it by simple vectors like this. Okay, means that this is your actual y minus your predicted y. Okay, this one is a predicted y. In other words, this one can also represent your y bull head. Okay, where I get this one? Okay, this is the y. This is the y. This is the things that I get that expression. Okay, so if this, okay, that is how you form or you establish your error vectors. Of course, if you want to know how good your expression here, or your linear equation here fit with your data, you need to total up all the error. Okay, means that you must E1 plus E2 plus E3 and so on. So that is one things that you need to do. But of course, if you total up directly like that, it's not good, because you can see that the error can be negative number, can be positive number. So one way you can avoid that is, okay, you know, if you want to make sure that the distance is just a positive number, okay, this is the reason why we are, you know, measure or we calculate the E1 square, then E2 square. So you make all things become square, because if you make everything become square, doesn't matter is it negative or positive, it will become positive value. So once you get all these things, so to measure the total error, I just write like this: total errors then is equal to your E1 square plus E2 square plus E3 square until your EN square. Okay, so if your data is something like this, and then you have a straight line and fit and, you know, overlap to all given data, then your E is equal to 0 and your total error is equal to 0. So this is the best fit. Okay, it means that 100%. If you talk about the R square, this is the where the R square equal to 1. Okay, I just want to relate this one with your R square. But again, you can see that doesn't matter is it R square or by using cost function, the mechanism is similar to find out whether that your to measure the goodness of the fit, or to see or to observe whether your equation is fit with the data, whether you get the best fit with the given data. Actually, it's almost similar. Okay, R, you must make sure the value is close to 1. But if you talk about the cost function here, the total error must be, okay, the total error here must be close to 0. Okay, so it means that you need to minimize your errors here. Okay, so if you talk about this one, this is what we call as a, okay, when you are measuring something like this, this is also called as a least square cost function. Okay, least square cost function. Okay, which is this one, least square cost function, meaning that you are square all the error and you total up the error. So that's why you call this one as a least square cost function. And other name for least square cost function is also known as a SSE. Okay, what is SSE? SSE is a sum of square error. Okay, so if you define your cost function as a sum of square error, this is how it's look like. So why do we call it as a sum of square error? Of course, you are square your error, then you sum up together. So that's why we call it a sum of square error. And later we will see that there's another cost function as well. Okay, it's not just a sum of square error. We also have some other cost function which is called MSE. Okay, this is known as a mean square error. Okay, mean square error. Okay, of course I will highlight this one later in when we learn about artificial neural network, but in the meantime, what we compute here is actually a cost function, but it's not just a cost function. The mechanism of measuring, you square the error and you total up, you sum up all the square error, that is called as a SSE. Okay, the square function name is SSE, which is sum of square error, and or other name for this one is a least square cost function. Okay, so you can see here, so by total up together like this, okay, if you want to form it in a matrix or in vector, this mechanism is look like this one. Okay, this one. So why I said like this, because if you remember, if you transpose your E, okay, if you transpose your E, it's become like this one, E1, E2 until En. Okay, your E your E transpose, okay, should look like this, E1, E2, E3, and so on. And then let me delete this one because we want to have space there. Okay, and then your E is this one, E1, E2 until En. Okay, this one also En. So if you multiply between this one and this one, as what we see over here, it's not a multiply, it's a dot product between two matrices, E transpose and E. Actually, it look like, okay, it's equal to your, the mechanism is similar to your E1 square plus E2 square until En square. Okay, you are plus together because this one multiply with this one, plus this one multiply this one, plus this one multiply this one, so you end up in this kind of operation. Okay, so if you write it in summation form, it should be look like this. Okay, just a small mistake there, it should be square here. Okay, it says square there. So in other words, that is also represent, okay, this one is represent your total error, which is this one. Okay, so I hope you clear about that. So that is one way to know whether the produced linear equation or linear regression is how good the linear equation fit with your data. Okay, of course, if the equation is bad, then the cost function is you get a higher value. So our objective, we want to make sure that our cost function produce as close as minimum value, or the best one, it should be equal to 0. Okay, means that there's no errors. Okay, so let's go back to this discussion because we not finished yet about this slide. Okay, so at the end, this is how the cost function look like. Okay, in general, they always use the notification, or they use a J there to represent your cost function. So your J is your cost function, where the definition of your cost function is a summation of your actual data minus your predicted data. Okay, this is your y head I, and then you square because you want to avoid the positive numbers. Then you want to avoid the negative number that we produce by this value. That's why you put square, and you total up together to get a total error. Okay, that is how we define the total error, or which is also known as our SSE, or least square cost function, which is this one. And of course you will ask, why you have 1/2 there. Okay, there's a reason to put 1/2 there. It doesn't matter. Okay, you can also delete this one. Okay, you just delete this one. That is actually that is known as the SSE, or least square error function. But we just put one constant, which is 1/2. There's a reasons there. Okay, later we want to simplify the derivation, so that's why we just put some some fixed number, which is 1/2 at the out part of this expression. Of course, the original part, this one still not changing. The one that is changed is only this one. You are added one fixed numbers there. Okay, but you can see that how we represent the cost function by having this cost function. This is the cost function. You can represent in this way, and then if you extend it into vector, it will look like this one. And you extend, if you simplify this thing, you will sure that you can see that this is how it should look like. Okay, so later you can try to find out how can this one extend into that expression, and then extend into that expression. You may refer to the previous slide how actually we replace, or we use the information from the previous slide to extend that equation. Okay, I don't want to discuss this thing more details. Okay, because there's a reason why I discuss this thing. One is to make sure that you familiar with the notation, okay, matrix notation or vector notation in linear regression, as well as logistic regression. And I also want to show you that actually how they optimize and find how they find the best linear equation that fit with the data by using the information from the cost function. Okay, this is some example of the cost function. Okay, you can see that what happens there. You can see this is your example of the data. It's a one variables input data. So you have B0 and not B0, beta not and beta 1. Okay, this one should be 1. I forget to put there. It's a beta 1. So let's say this is after you set with the fixed beta naught and beta 1. This is how you generate the lines, and then this part over here is just a equation, or to plot the relation between your beta naught, beta 1 and the cost function. Okay, so you can see that the one that inside here is a minimum value. The ones going toward that way, okay, it's become highest value. Okay, going towards that way is going to increase the cost function. So what happens there? Let's say this is your function. So if this is the data, if you set your B0 and B1 and generate these lines, and if you measure the errors, this is you produce the J there at this position. And then if you plot another way, or you set another way, which you change the B0 and B1, okay, this one is B1. So you find out that, by setting different B0 and B1, you realize that the value here is keep changing. And again, like I said before, this one should be the bad linear equation, because linear regression generated, because it's far from what we expect. So that's why you can see that the cost function here going towards this line, because this line is actually is a region that produce the highest cost function. Okay, the one that minimum is this point. So again, if you put any randoms B1 and B0, like this one, or this one, okay, then it will still give you some cost function. But at the end, what we want here, in order for us to find the best, of course, if we talk about our objective, the main objective, if we want to find the linear regression model that can fit as best as possible with the given data. So of course, the one that best is this one. Okay, this one. because this is the one that you can, this is the one that you can obtain, which is the cost function is as small as possible. So that's why you can see there the cost function there at the center, where it's already occupy at this minimum values at this cost function graph. Okay, so as you can see there, this how this equation work, meaning that you can change your B0 and B1, but but of course you cannot, you know, do this one can be done iteratively, but of course if you just, you know, select a random B0 and B1, it's almost impossible to you to achieve the one that is minimum, because if you talk about the randomness, then it seems to be some interactive, okay, you have some interactive mechanism, but it's not guided. Okay, that's why we don't know where actually this B0 and B1 is going towards, whether to whether it's become worse or it become good. Okay, that's why it's we cannot just, you know, simply generate random number and put set as your B0 and B1 in order for you to find the best one. Okay, there's some mechanisms there, but I just want to show you over here that is what is mean by cost function. So the cost function here is actually we want to measure how good our linear regression models, and if our linear regression model produce the higher cost function, then we need to revise back the B1 or B0 parameter, so it can be changed. So once it change, it can going to the minimize the cost function, okay, going to reduce the cost function. But how we can do something like that? Okay, that's why the one that you learned before, if you remember, this is what we call as one way to find the best linear regression model that fit with your data set. You learn one method which is called least square method. Okay, so what is least square method? Of course, this is how it's calculated, but I will like to in next video lecture, I will like to highlight how come this how they produce this formula based on the information from the cost function. Okay,